Good morning, everyone. Welcome to my talk. Before getting started, please allow me to introduce myself. I'm Thodoris Sotiropoulos. I come from academia. I'm a postdoctoral researcher in the Advanced Software Technologies group at ETH Zurich. In my research, I develop tools for developers. Tools that make developers' life easier. In particular, in my research, I develop tools such as bug-finding tools, static analysis tools that assist developers in ensuring the reliability of their programs. And to do so, I primarily use programming language technologies such as formal methods, program analysis, or randomized testing. In this talk, I will focus on the problem of the reliability of compilers' type checkers. We'll see what kind of faults are prevalent in compilers' type checkers that you might not aware of, and we'll see their impact. And in the second part of my talk, I will briefly present two bug detection and prevention techniques, namely EEST and Falia. So let's begin with the basic things first, compilers. A compiler is software that takes a program written in a high-level language, such as Java, and produces a program written in a low-level language, such as Java bytecode, x86 assembly, and then the output program is run on your machines, a virtual machine, whatever. And the input program is passed across different compiler phases. For example, initially the compiler tokenizes the input program. It produces the corresponding abstract syntax tree. On top of that, it performs various semantic analysis that determine the correctness of the input program. And then the compiler eventually proceeds with the middle end and backend when the actual code generation is done. This talk is not an introduction to compilers, I promise. We will focus on the type checking process of this pipeline. So a type checker takes an input program and based on the type system of the language and some other semantic rules, it determines whether the input program is correct or incorrect. And if the program is incorrect, it also produces a report with all the errors included in the program. A brief note here, a type system is just a set of rules of the main types of what the main types of language are, what kind of operation on these types are valid, how these types relate to each other, and how they can be combined. Type checkers are the most widely used form of static bug detection. We use them every day in order to identify bugs in our programs. A fundamental property of type checkers is soundness, meaning that once a program type checks, then there are no type errors at runtime. So this ensures the property of type safety. This property is captured by this quote by Robert Milner, a famous computer scientist: well-typed programs cannot go wrong. We can say that sound type checkers is a form of verification because they verify the absence of certain class of errors, in particular type errors. So type checkers are programmed, and just like every software, they might contain bugs. We saw yesterday with the example of Java that languages are constantly evolving. They are constantly adding new features to the language that should work smoothly with the older features, and this adds complexity to the type systems and the language itself. So they type checkers might contain bugs. But what happens if we have a buggy type checker? And what's the impact of these faults? We will name these faults compiler typing bugs. So let's begin first with crashes. So in this case, we have a program. We give this program to a buggy type checker, and then suddenly this type checker produces a crash with a huge stack trace that makes no sense to the user of the type checker. How many of you have encountered a compiler crash before? Of course, crashes are frustrating to developers because a compiler should never crash no matter the input, right? Another class of compiler typing bugs are unexpected compile time errors. So in this case, we have a well-typed program, a program that respects the semantics of the language. And we give this program to the buggy type checker, and the type checker says, no, your program is ill-typed, and produces a corresponding message. So in this particular example, although our program is valid, right? We try to assign an array of integers to something that expects an array of ints. The compiler mistakenly reports that in compatible types, an array of floats cannot be converted to an array of ints. These type of errors are very annoying to developers because they make them waste their efforts in debugging their correct programs. They believe the error message produced by the type checker, and they try to identify what they did wrong. And they try to seek for workarounds that type check. Another more scary class of compiler typing bugs are unexpected runtime behaviors. So in this case, we have an ill-typed program, an invalid program, and the buggy type checker says that your program is correct, it produces the corresponding executable, but when we run the executable, strange things happen. In this particular example, this exam program is invalid because notice here that we try to assign an object of type A into a variable of type B, while type A is not a subtype of type B. And when we try to perform this field access, we experience this runtime exception, no such property F for class A. Of course, this error should have been caught by the type checker at compile time. So, of course, this class of errors breaks the soundness of type systems. Unexpected runtime behaviors are very difficult to diagnose and debug, and this class of errors also raises security concerns, especially if we deal with type-unsafe languages like C. Moving forward, we have also misleading reports. In this case, we have an ill-typed program. The compiler, the type checker agrees, your program is indeed ill-typed, but it does so by producing a wrong diagnostic message. For example, in this particular example, although in this program we have a type error, because we try to assign an array of floats into something that expects an array of ints, the type checker produces an error message that has nothing to do with the actual error included in the program. And this type of bugs are very confusing to developers because type checkers suggest ineffective fixes, and they hide other program errors like that example we saw. And finally, we have compilation performance issue. In this case, we have a program, and the type checker takes much time to process even the simplest fragment of code. And in many cases, it never terminates. Of course, this wastes developers' times and resources. Okay, we have seen plenty of exams. So you might wonder, these are extreme cases. They can never happen in real-world scenarios. Okay, now I'm going to show you two real-world bugs that were found in the compilers of Kotlin and Java. So we begin with a Kotlin bug, where the Kotlin compiler mistakenly rejects a well-typed program. In this Kotlin program, we create a list of strings, and later we apply function map in order to update another list containing instances of class A. Function map is a polymorphic function. It defines two type variables, I and O, and it expects a function that maps values of type I to values of type O, and the final outcome of function map is a list containing instances of type O. In this example, the compiler needs to properly instantiate this type variables with concrete types. So we need to instantiate type variable I and type variable T with type string, because we apply function map to a list of strings, and we need to instantiate type variable O with type A. We give this program to the compiler and rejects the program by saying not enough information to infer type variable t defined in this generic class. In a situation like this, the compiler tries to properly instantiate these type variables by building a type constraint problem. But due to a bug, the compiler builds the wrong type constraint problem and and as a result, we see this error. Let's proceed with the second example. Here we have a Java program. We define a polymorphic interface. We define a second interface that inherits from the first one, and later we define a class that implements the second interface. And the body of this class, we have a polymorphic starting function that defines a type parameter whose upper bound is b wildcard, and the body of this function has a method call. We need to type check this method call. So the compiler sees that the type of the receiver is type parameter t, whose upper bound is b wildcard. So now we need to type check the argument. We pass something that is of type array of strings, but the expected formal parameter type is an array of x's, where x is a first type variable. So the compiler needs to instantiate this type variable with a concrete type, but due to a bug, instead of replacing this type variable with a capture type, because notice the receiver is b wildcard, it to replace this type variable with the upper bound of this capture type, which is type object. So we expect now something of array of objects, and we pass an array of strings. Arrays in Java are covariant, so an array of strings is a subtype of array of objects, so the compiler permits this call. When we try to the compiler permits this call, produce the corresponding executable. We run the executable, but unfortunately we get a class cast exception. String cannot be cast to integer. Of course, these type errors would have been caught by the type checker at compile time. So we saw that these kind of bugs can happen in real-world compilers, and we wanted to study more real-world compiler typing bugs, and we studied 360 bugs from the compilers of Java, Scala, Kotlin, and Groovy, and we get some statistics. So in this figure, we see the distribution of these types of bugs. Compiler typing bugs have diverse manifestations that span from compilation to runtime, and we observe that unexpected compile time errors are the most common types of bugs. But we also observe that crashes and unexpected runtime behaviors are also common. Regarding the root causes, the primary root cause lies in the type-related operations implemented by the type checker. So a type checker implements various type-related operations like type inference, subtyping checks, computation of least upper bounds. These type of operations might be faulty, especially if we deal with a sophisticated type system. We also examined the characteristics of the bug-revealing programs, the programs that trigger these bugs. And on average, these programs are pretty small, consisting of 10 lines of code. And the interesting bit here is that around 1/3 of compiler typing bugs is triggered by invalid programs. We also examined what kind of features exhibit in the bug-revealing programs, and we see that features related to parametric polymorphism, so for example, the program uses polymorphic types or declares a polymorphic generic class or generic function. If we have such features, then it's more likely to trigger compiler typing bugs. And this finding is similar across the studied compilers. In total, more than half, 57% of the bug triggering test cases involve features related to parametric polymorphism. So we can say that parametric polymorphism is hard to get right, and it's the feature with the most bug triggering capability. So a question arises at this point. How can we detect this kind of faults? And how can we do that through automated means? In order to answer that, let's see what we already have. Compiler testing is a research area that has really thrived over the past decade, where we have witnessed effective techniques such as C-Smith. How many of you know C-Smith? C-Smith is the most well-known program generator for C programs. And it has uncovered thousands of bugs in industrial strength compilers like GCC and LLVM. So we can use traditional fuzzing techniques. So these techniques works as follows. So they might take some existing programs taken, for example, the compiler's test suite, and they mutate this program in some way in order to derive new test cases. Alternatively, a fuzzing technique can take a grammar, the grammar of the language, and in this way it generates programs that respect the grammar of the language. The generated programs are given to the compiler and the test, and we identify bugs. What's the problem here is that the discovered bugs are not deep, because these techniques struggle to get past the parser or generate programs that are nearly semantically valid. Why is that? Because these techniques know nothing about the semantics of the language and the test. And they can only detect crashes. Why is that? Because they face one of the most well-known problems in the literature of automated testing, that is the test oracle problem. Let me explain. The test oracle problem is that, consider that we have a program generated by a fuzzer, and we give this program to the compiler and the test. The compiler produces an output. There is no way to determine whether this compiler behavior is the expected one or an unexpected one. And in this way, we are unable to detect unexpected compile time errors or unexpected runtime behaviors, because there is no guarantee that the generated programs are valid or invalid. Thankfully, there are some techniques that help us address the test oracle problem. One of them is called differential testing. The idea of differential testing is very simple. So imagine that we have an input, a program, and we pass this program to at least two equivalent compiler implementations, compilers that implement the same language standard, like GCC and CLang. And imagine that the one compiler says that your input program is well-typed, and the other says that your input program is ill-typed. Then there should be an error in one of these compilers. What's the problem here? Is that differential testing requires at least two equivalent compiler implementations. Unfortunately, this is not always the case. To address this, we have another testing technique called metamorphic testing. I will particularly focus on one instance of this metamorphic testing technique called equivalence modulo inputs. This idea is very beautiful and simple. We have a program. We give this program to a compiler. The compiler produces an executable. We run the executable, and we track the output of the executable, and at the same time, we monitor the execution of the executable to identify the live and the dead regions of the executable. Then we mutate the dead regions of the executable by injecting some additional code or removing some code, and then we have a new program. We pass the new program into the same compiler. The compiler produces a new executable. We run the executable by using the same input as the original executable, and we track the output. Since the only modifications we did are in the dead regions of the program, then we expect that running the same executable, running the new executable under the same input will yield the same results as the original program. If this is not the case, then there is a bug in the compiler. This technique has been shown to be very effective. It has found thousands of bugs in GCC and LLVM, but unfortunately, it targets optimizing compilers, meaning that it finds bugs in the optimization phase of compilers. So it finds miscompilations, cases where the compiler generates the wrong assembly that does not match the semantics of the original source program. So our initial question remains, how can we detect compiler typing bugs through automated means? Conventional fuzzing techniques face the test oracle problem. Differential testing requires at least 2 equivalent type checker implementations. Equivalence modulo inputs targets optimizing compilers. Well, an important aspect of research is to study and observe. And if you think about it, this is exactly what we did before, where we examined actual compiler typing bugs found in real-world compilers. And through this bug analysis examination, we can derive a bunch of interesting observations and findings that can provide us with insights on how to build proper tools that help us improve the reliability of type checkers. And this is what we did. And based on these findings, we developed EEST and Falia. Let's begin first with EEST. For those who don't know, EEST in Greek mythology was the smith god, and Falia was one of his daughters. So, again, we have our findings and observations. Compiler typing bugs mainly manifest as unexpected compile time errors, or we have that parametric polymorphism is the feature with the most bug triggering capability, and so on. And based on this finding and observation, we designed EEST, a framework that consists of a generator. This program generator produces program written in an abstract language, a very simple object-oriented programming language that supports parametric polymorphism and type inference. And why do we generate programs in our abstract language? Because our goal is to test multiple compilers. And these programs are well typed by construction. So the test oracle is baked into the program generator. So the expectation here is that if the type checker rejects a program generated by EEST, then there is a bug in the compiler. And on top of our program generator, we have developed 2 mutations as an effort to find type inference and soundness bugs in the compilers. I will say more details about those mutations later. The outcome of our program generator and our mutations is passed as input to language-specific translators who are responsible for converting a program written in the IR, in the abstract language, into concrete source files, such as Java source files. These source files are passed as input to the compiler and the test, and based on the given oracle, we check the compiler output for bugs. Here is the overview of the features supported by EEST IR. So the generated program exhibit features related to parametric polymorphism. So they contain generic class declaration, generic function declaration. We have standard language features like conditionals, object-oriented programming features like inheritance, functional programming features like lambda expressions and method references. But based on our findings, we prioritize features that are more likely to trigger these compiler typing bugs, such as parametric polymorphism. And let's go back to our mutations. We have developed 2 mutations. The first mutation is called type erasure mutation. It takes a well-typed program, and then it erases types from the program while preserving the program correctness. So the mutated program is still well-typed. And why do we do that? Because in this way, we want to stress test the implementation of type inference procedures implemented in the type checker. In this particular example, We just removed the two type arguments from these two polymorphic constructor calls, but the program is still valid because the compiler is able to infer these missing type arguments from the surrounding context. The second mutation is called type overriding mutation. It takes a well-typed program and injects a subtle type error in the program by replacing a type with another incompatible type, meaning that the new type is neither a subtype nor supertype of the old type. And we do that in order to find soundness bugs. So the new program, the mutated program, is no longer valid. And with EEST, we were able to detect more than 150 issues in type checkers of popular languages such as Java, Kotlin, and Groovy. Let's have a quick demo. So now I'm running EEST to generate 10 Java programs. So after EEST terminates, it creates a directory where all the generate programs are stored. This is how a program generated by EEST looks like. As you see, it's complex. It contains type-intensive operations, complex types, like wildcards, polymorphic types, bounded polymorphism. This particular program is around 300 lines of code, consists of 300 lines of code. And we can use EEST to generate programs in different languages. So I'm going to use EEST to generate Scala programs. Oops. Currently, EEST supports Java, Scala, Kotlin, and Groovy. Again, okay, this is the generated Scala program. And notice here that with this option, I enable the type erasure mutation. Let's see how a program generated by the type erasure mutation differs from the original one by running a diff command. As you see here, the mutated program has missing type information. Here, for example, we remove the declaration type of this nitpick variable because this type can be inferred by the type of the expression found on the right-hand side of the assignment. And we perform similar mutations in the remaining parts of the program. But what are the limitations of EEST? The problem is that we exercise features that support it. We can exercise only features that are supported by EEST IR. So if we want to exercise, for example, the implementation of static methods, we are unable to do so because this feature, for example, is not supported by EEST IR. So this means that if EEST can easily saturate and at one point we are not able to find more bugs. And okay, one can say that we can just extend EEST to support these missing features. The problem is that building a useful generator is technically hard. It's not easy, believe me, it's not easy at all, because these features have unpredictable effects with other features, and in many cases, we need to sacrifice diversity in order to accommodate all these features into the generator in order to produce well-typed programs. And this involves engineering effort. So how can we deal with that? Again, we can leverage a finding from real-world observations. This is a finding that I didn't mention before. Roughly 1/3 of the bug triggering programs invoke the standard library, for example, collections API, like the Kotlin program we saw before where we created a list of strings. And based on this observation, we created Falia. Falia stress tests the implementation of type checker by leveraging existing APIs and creating complex Scala programs that invoke these API components. So Falia takes an API from an existing software library. This can be the standard library or any other third-party library. And then it generates a program. The generated program is pretty small. It just creates an expression that invokes components from the given API. So in this case, we create a method call that invokes method m, and this method is supposed to be included in the given API. And the oracle here is baked into the program generator. So we generate well-typed programs by construction or ill-typed programs by construction. And let's see 2 real-world bugs detected by Falia. So here we have a Scala program, and we use the Guava library, a famous Java library that extends the Java collections framework. So in this Scala program, we create a tuple that contains instances of this link-hash multiset class, and later we access the first element of the tuple, and we call the method retain all. We give this program to the compiler, this simple program to the compiler, and the compiler crashes. Let's take a look at the definitions of this Guava library. So this retain all method is defined in an abstract class inherited by the link-hash multiset class. Notice here that this abstract class has a default access modifier, meaning that this class is not accessible via code outside this package. However, this retain all method has a public access modifier, meaning that this method is accessible by any public subclass of this abstract class, including link-hash multiset. However, Dotty, the Scala 3 compiler, mistakenly believes that this method is not accessible, and this triggers this crash. Here is another example. We have a Groovy program, and we use an Apache library to remove some elements from an array of bytes. We give the program to the compiler, and the compiler rejects the program by saying this method call is ambiguous. Let's take a look at the definitions included in the array utils class. We see here that we have a bunch of overloaded definitions, all of them operating on an array of primitive types, and we also have a polymorphic definition that operates on arrays of reference types. Although it's clear from the code that our intention is to call the overloaded variant that operates on arrays of bytes, the compiler thinks that this method call is ambiguous and rejects the program. The bug lies in the way the compiler handles variable arguments and arrays of primitive types. With Falia, we detected more than 80 issues in type checker of popular languages such as Scala, Kotlin, and Groovy. And what are the benefits? Why does this approach work? What are the benefits of API-based programs? Let's think about that. Libraries are written by experts. They tend to be general, and they make heavy use of complex language features such as parametric polymorphism, overloading, etc. So we can build a program generation process centered around APIs, so we can generate complex and well-typed definitions. We are able to generate a program generation process centered around APIs without the need to generate these complex and well-typed definitions on ourselves. So we get rid of the most difficult burden, the generation of complex and well-typed definitions. And this provides us with rich feature coverage for free. Another benefit is applicability, because APIs are available to every mainstream programming language. It enables efficient testing, because now the type checker takes less time to consume smaller programs than larger ones. And it also facilitates test case reduction because it's easier to reduce smaller programs than bigger ones. And how can we generate interesting client programs with Falia? I will briefly explain the high-level idea. So we try to encode every definition included in the API, method definition, field definition, into a sequence of types. So this particular method is encoded as a triple. So here, this triple says that in order to call this method, we need a receiver of type A because this method is included in class A. We need to use a parameter, an argument of type B, and the expected type of this method is type B. And of course, these sequences form skeletons of expressions. And yeah, in order to call this method, we need any expression of type A, and we need to pass any argument of type B. And actually, we generate all the different ways we can invoke a particular definition using different typing patterns. And to do so, we take the subtypes of the receivers, the subtypes of the parameter type, and the supertypes of the expected type. We take the Cartesian product, and we generate all the different typing combinations. So for example, in the first case, we call the method M using any expression of type A and a parameter of type B. And in the second test case, we use a receiver of type B. And this test case is still valid because notice here that type B is a subtype of type A. And we do that in order to stress test the implementation of subtyping checks in the type checker. And our final step is to concretize these skeletons by using a function called gamma that takes an internal representation we call API graph and a skeleton, and it fills the holes, these missing holes, with concrete exceptions. So here we fill this hole with an expression of type A. And in order to do that, the problem is very simple if we don't have parametric polymorphism. So here is the API graph. And the meaning here, in the nodes of the API graph are either types or definition. Boxes indicate definitions, like methods, and circles indicate types. The meaning here is that, for example, take this definition. This edge indicates that in order to call this getInt method, we need a receiver of type A, right? And this edge here means that the outcome of this definition is type int. And imagine now that we have the problem of finding inhabitants of type int. What do I mean with that? Is we want any expression whose type is int. We can answer this question very easily by identifying all the paths in the API graph that lead to type int. Any path corresponds to an expression. This particular example results to this chain of method calls, and the result of this method calls is a value whose type is int. Of course, this problem becomes much trickier if we deal with parametric polymorphism. I don't want to be too technical here. If you are interested in that, talk to me during the break. I will have a brief demo of Thalia. We said before that the input of Thalia are APIs. So I can use some example APIs, for example, the standard library of Java. We have plenty of classes here. Let's take a look. So we see the API of buffered input stream class. Here these APIs are encoded into the JSON format. This class inherits from this class, and we know what kind of methods are defined in this buffered input stream class. For example, we have a method read that takes three parameters, an array of bytes, 2 integers, and return an integer. Okay, we have these APIs, these JSON files. These files are given as input to Thalia, and we can run to generate 10 Groovy programs. This is the program generated by Falia. It invokes components from the given APIs. Here is the second one. Again, we use various components from the given APIs. Over a period of 3 years, we have found more than 160 issues in the compilers of Groovy, Kotlin, Java, and Dotty using Thalia and Hephaestus, out of which 135 issues have been fixed by developers. Most of the discovered features are unexpected compile time errors, but we also detected some soundness bugs and crashes. And we have interacted with compiler development teams. Our efforts have been acknowledged by the release notes of programming of compilers. Here, a fragment from the release notes of Groovy. This work was done in collaboration with various colleagues from Greece, the UK, Imperial College London, and of course, Switzerland, ETH Zurich. This is the page of our project. You can follow this link if you want to learn more details about the project. Feel free to talk to me during the breaks. I would be more than happy to provide you with more details about the project. Thank you.
Thank you, Thodoris. Thank you for your informative presentation. And guys, you have such an opportunity now to reach out to Thodoris and ask him your questions. But we are going right now for a short break, so please come back at 10:50 and we will continue with our next speaker. Enjoy your break.